So good day everyone. So for today's topic, it is all about force and pre-vibration. So let's start. So what is pre-vibration? So if a system after an initial disturbance is left to vibrate on its own, the ensuing vibration is known as pre-vibration. So no external force acts on the system. The oscillation of a simple pendulum is an example of pre-vibration. So pre-vibration is where there is no externally applied vibrating forcing. So meaning in pre-vibration, energy will remain the same and energy is not added or removed from the body. So the body keeps vibrating at the same amplitude. So other examples of oscillations connected to a horizontal spring, the sound produced by a turning fork in a short distance. So there are three types of pre-vibration: the longitudinal vibrations, the transverse vibration, and the torsional vibration. So let's take a look onto the three types of pre-vibration. So the first one is the longitudinal vibrations. So as you can see, that these move parallel to the axis. So for the transverse vibration, so the disc moves perpendicular to the axis. So for the last one, the torsional vibrations, so the disc moves in a circle about the axis. So now let's go on to the undamped free vibration. So undamped means that there are no energy losses with the movement. So an undamped system will vibrate forever without any additional applied forces. So one example of this is a single pendulum that has very low damping and it will swing for a long time before stopping. So in addition, damp means that there are resistive forces and energy losses with the movement that cause the system to stop moving eventually. So next one is free. So means that after the initial perturbation, the only forces acting on the system are internal to the system and or gravity. So a tuning fork continues to vibrate after one initial perturbation. So force means that there is an external, typically periodic force acting on the system. So one example of this is a jackhammer that vibrates due to having a supply of compressed air eventually continually forcing the beat up and down. And it stops vibrating very quickly without external periodic forcing. So we can derive the equation of the system by setting up a pre-diagram. Consider a mass sitting on a frictionless surface attached to a wall by a spring. So first one, the system above is in equilibrium. It is at rest and it will stay at rest unless some other forces acts on it. So next one is to start the system vibrating. We need to perturb it. With perturbation is moving the system away from the equilibrium by a small amount. So next is when we perturb this system, we stretch the spring. This generates a spring force and the spring force is always in a direction that tends to pull the system back toward equilibrium. So mass spring system perturb perturbed by amount of x from the equilibrium. So this stretches the spring, causing a spring force which tends to pull the mass back toward equilibrium. So next is the mass spring vibration. After an initial perturbation, the system oscillates between two extreme positions. So the extreme positions are turned around points where the velocity is zero, but the spring force is maximum, and therefore the acceleration is maximum. So now let's go on to the force vibration. So if a system is subjected to external force, often a repeating type of force, the resulting vibration is known as force vibration. So the oscillation that arises in machines such as the diesel engines is an example of force vibration. So the frequency of the external force coincides with one of the natural frequencies under frequencies of the system, a condition known as the resonance occurs, and the system undergoes dangerously large oscillations. Failures of such structures as buildings and bridges, turbines and airplane wings have been associated with the occurrence of resonance. So enforced vibration meaning is when a time-varying disturbance is applied to a mechanical system. So the disturbance can be a periodic and steady-state input, at a transient input or a random input. So the periodic input can be a harmonic or non-harmonic disturbance. So example of these types of vibration include the washing machine shaking due to the imbalance. So transportation vibration caused by an engine or an even road, or the vibration of a building during an earthquake. So for linear systems, the frequency of the steady state vibration response resulting for the application of a periodic harmonic input is equal to the frequency of the applied force or motion, with the response magnitude being dependent on the actual mechanical system. So last one is the force damp motion. So a real system does not exhibit idealized harmonic motion because damping occurs. So as you can see in figure 1, a spring mass system with dampener. So consider a mass spring system consisting of a mass M and spring with the Hooke's constant K with an added dashpot or dampener. So depicted in figure 1 as a piston inside of a cylinder attached to the mass. So a useful physical model for purpose of intuition is a screen door with a door closer. So the closer has a spring and an adjustable piston cylinder style dampener. So that is all for our topic today. Thank you for listening.